Imagine booking seats at a movie theater. You need 5 seats together for your group. That is exactly how an array works in a computer's memory. It finds a contiguous block of empty space, claims it, and locks it down. But what if a friend decides to join late and they want to sit right in the middle? In an array, you can't just squeeze them in. Every single person sitting to the right has to stand up, grab their popcorn, and shuffle over one seat just to make room. In computer science, this shifting is measured as big O of n time, a notation meaning the delay grows directly alongside the amount of data you have to move. There is a different way to organize this information. Imagine instead of fixed theater seats, your data acts like a train. If you need to add a new passenger to a train, you don't force everyone to walk down to the next car. You just roll a brand new compartment onto the track and snap it into the middle. This is the core mechanism of a linked list. By separating the information from its physical order in the computer's memory, we've removed the strict limitations of an array. The data no longer needs to sit side by side. It only needs to know how to find the next piece. We use a building block called a node, built from 2 parts. The payload, defined as int data, holds your information. The mechanical hook is a pointer, node * next, storing the exact memory address of the following train car. Because each car carries its own map to the next one, your computer can scatter these individual nodes anywhere there happens to be free space. The memory manager never has to force them to sit in consecutive order. Let's see what happens when we want to insert a brand new piece of data precisely into the middle of this sequence. To add car B between original cars A and C, we do not move heavy data. We simply sever the pointer extending from A. Then we aim A's pointer at B and B's pointer at C. The chain is complete. Deleting a piece of data works with the exact same unhooking logic in reverse. If we want to remove car B, we tell A's pointer to bypass it entirely and link straight to C. Car B is isolated and safely discarded by the system. Changing the direction of a pointer takes almost zero computing power. Because we aren't physically shifting thousands of items like we had to with the cinema seats, adding or removing a node anywhere in the chain happens in O of 1 time. What we have built so far is a singly linked list, running in exactly one direction. It reads from left to right until the final pointer hits a dead end called null. If you add a second mechanical hook to the front of every train, doubly linked list. This grants developers the ability to traverse the data backward as well as forward. And if you take that final dead-end pointer and loop it all the way back to the very first engine, you get a circular linked list, allowing the system to cycle through the data continuously. Adding these extra hooks gives you more navigational control, but it comes with a trade-off. Every new pointer you add consumes a little bit more of the computer's available memory. No matter which variation you build, the entire chain relies on one single variable, the head pointer. This is the entry point, the absolute only coordinate your computer has to find the start of the list. If you accidentally overwrite the head pointer in your code, you completely lose the map. The engine detaches. The rest of your data is still sitting out there in memory, but the computer has no way to reach it. This stranded, inaccessible data is a critical error programmers call a memory leak. Avoiding these errors takes practice, which is why linked lists are common in technical interviews. One frequently tested algorithm is the 2-pointer, or fast and slow pointer technique. You place 2 markers at the head. One moves forward 1 step at a time, while the other jumps ahead by 2 steps. Because the fast pointer travels exactly twice the speed of the slow one, by the time the fast pointer hits the end of the track, the slow pointer will be resting precisely on the middle node. This specific fast and slow pattern allows you to find exact midpoints or detect hidden infinite loops without having to count every single car. This matrix compares arrays and linked lists, summarizing the trade-off. You use linked lists when you need immediate O1 insertion and deletion, but if you need to quickly search for a specific item, arrays win, because searching a linked list forces you to walk through every single node from the beginning. Learning how to manipulate these pointers shifts your focus from the data itself to the architecture that holds it. It provides the foundation for managing memory manually, a requirement for building custom, dynamic structures that can grow and shrink in real time.